Hello everyone, Mrs. Hanson once again, picking up with our Chapter 8 lessons. As described, we're going to be investigating concentration units, looking at percentages such as weight by volume or volume by volume, and turning our attention then to molarity in the next section. So in our note packs, we're going to define concentration. It's really telling us how much solute is dissolved in a given amount of solution. Weight by volume is one type of percentage. You'll see that written as W over V, representing weight by volume percent. How many grams of solute in 100 milliliters of solution expressed as a percentage? And that's called a weight by volume percent concentration. Grams of solute over a volume of solution expressed as a percent, so times 100. A mass over volume percentage. For example, if I see vinegar and it contains 5 grams of acetic acid, so notice that this would be called the solute. It's what you have the least of, and it's in 100 mils of total solution. Remember how we just think of part over whole representing percentages. That would come out to be 5% weight over volume for acetic acid, 5% solution. Mass over a specific volume tells us its percentage. So let's take a peek at some examples and see what these would look like. Chloraseptic sore throat spray is 0.35 grams of the antiseptic phenol dissolved into 25 milliliters of solution. We have our grams of solute over volume of the whole solution, and we simply express that as a percent. To solve for this gram over mil, we would hit 0.35 divided by 25 and times 100 to express it as a percentage. This is 1.4% weight by volume. And that's that. Giving grams of solute divided by the volume of solution expressed as a percent, 1.4%. And then you'll see that W over V representing a weight by volume percentage. Should we try another? These are kind of fun. In a commercial mouthwash, we have 4.3 grams of the solute called ethanol and 0.021 grams of another active ingredient of antiseptic in each 30 ml portion. So we have 2 different solutes being dissolved in a 30 ml portion, and that would be the volume of the solution. Calculate the weight by volume percentage of each component. So we need 2 answers, don't we? 2 separate answers. So the first solute would be 4.3 grams over the 30 mils expressed as a percent, and that would come out to be 4.3 divided by 30, and then I multiply by 100 to get my percent sign. It's 14.3. We should probably have 2 sig figs, so I'm going to put that as 14% mass by volume. And the second 0.021 grams in that same 30 ml quantity expressed as a percent, and let me hit that with you. My screen says 0.07, and I need 2 sig figs, so I'm going to have to put another 0 after that, and that ends up to be the percent, right? So 0.021 divide by 30 times 100, and it still is 0.070%, and be sure to just label that as mass by volume. So 2 answers there, since we wanted 1 complete concentration on each separate solute. How about another? What is the weight volume percent For sodium chloride in some seawater, if 1 liter contains 35 grams of sodium chloride. Well, the trick here is that we don't really want 1 liter down here. Instead, we have to have a milliliter. And so just keep in mind that this is the same as saying 1,000 milliliters. And we're going to then express it as a percent. So we're going to convert a liter to a milliliter for the calculation. Alrighty, so 35 divided by 1,000, and then you're going to move the decimal back 2 spots when you multiply it by 100, and this would be 3.5% mass by volume. 2 sig figs, yep, we got it. Good work. Another type of expression for concentration is a volume over volumes, and especially if we don't have a solid dissolving into the solution. If it's a liquid that is miscible in another liquid, you'll express it as volume percentages. For example, if we had a bottle of rubbing alcohol and it says that a 70 ml portion of our 2-propanol, that's isopropyl alcohol, and 100 mils of solution, it comes out to be 70% volume by volume. So you have a mil of solute over a mil of solution, and then express that as a percent, so multiply by 100. Notice again, we're using milliliters as our representative unit for mass and for volume percentages. So we have a 750 ml bottle of wine, and it contains 101 mils of ethanol. Remember that the mil of ethanol represents the solute. It's what you have the least of. The entire solution, we'll assume, fills the entire wine bottle, 750 mils. And we'll express that as a percentage and report volume over volume. 101 divided by 750 times 100, and you get 13.47. We need just 3 sig figs, so 13.5%, and then do this, volume over volume, so you know what those units are. Milliliter over milliliter. Here's another example. We have a 1 ounce bottle of lemon extract, and it contains 24 mils of ethanol. What's the volume concentration of ethanol? Well, I can't use an ounce, so I have to make sure that I'm putting in there that the fluid ounce is 29.57 mils in 1 fluid ounce. And that happens to be the size of this bottle, 1 fluid ounce. And so that's the equivalent of saying 29.57 mils. Do you see how they rounded? On the label it says 29 mils. But 1 fluid ounce, that's supposed to be a U, is equivalent to 29.57 mils. So let's use that more accurate description. So we have an active ingredient, ethanol, 24 mils. That's drinking alcohol. Did you know that lemon extract had so much alcohol in it? My goodness. And it's set over 29.57 mils. That's the volume of the entire solution, and we'll express that as a percent. 24 divided by 29.57 expressed as a percent. Wow, 81.163. Let's do what? We have 2 sig figs limiting us, so it's 81% volume by volume alcohol. That's why I said, wow, that's a high percentage of alcohol in lemon extract. It's 81% by volume alcohol. Who knew? Here's a saline solution used in intravenous drips for patients who cannot take oral fluids, and it contains 0.92% weight by volume of sodium chloride in water. How many grams of sodium chloride are contained in 250 mils of solution? I have no idea why I have ibuprofen picture on here when we're talking about an IV solution. Well, sorry, this is a distractor. Must be coming up for our next problem. Let's talk about the IV solution. It says 0.92%. And then it gives me this weight by volume. Now let's think about what that means. It means that 0.92 grams in 100 grams, or I should say mils down here, that's the definition of percent, right? Parts out of 100 parts. So that's what I wanted us to see, what this means. The percentage tells us 0.92 grams of sodium chloride are contained in every 100 mils of solution. So how many grams would we have in 250 mils of solution? I need to rewrite that. I ran myself right off the page. There are 0.92 grams of sodium chloride in 100 mils of the solution. I just want us to say that this is the definition of percent mass by volume. How many grams of solute in 100 mils of solution? We're asking ourselves, well, how many grams of sodium chloride would be contained if instead of 100, we had 250 mils of the solution? So we just set up a proportion. I misspelled proportion. There we go. Proportion. And we'll solve for cross multiplying. So we'll cross multiply the side without the variable, 0.92 times 250, set equal to 100 times x. So we're cross multiplying. Divide both sides by 100 and you'll isolate x. So my key sequence, 0.92 times 250, divide by 100. And I get 2.3 grams of sodium chloride. Is that the correct sig figs? Yep, 2 sig figs would be perfect. What volume of a 5% weight by volume solution of ketamine contains 75 milligrams? Okay, just want us to set up a proportion, set up a ratio so that you can see the expression. This definition means there are 5 grams of our solute, ketamine, in every 100 mils of solution. And I'm just going to write SOLN for solution. This is the solute over the entire solution. 5% tells me there's 5 grams of solute and 100 mils of solution. Well, notice here it says I'm looking for volume. So I know that my X is going to be how many milliliters, but I'm given 75 milligrams of this particular solute, 75 milligrams, but I need it to be a gram. So just make sure that you remember milli is 1,000 for every 1 gram. So I need to convert that by moving that decimal spot 3 spaces to the left. That is 0.075 grams of solute. And that needs to go in here so that I have the same units on both sides of the equal. So we have 5 grams over 100 mils set equal to 0.075 grams over x, where x is going to be the volume we're solving for. Now remember, we just cross multiply when we're pulling out the x when we set up a ratio. So 5x will be equal to 100 times 0.075. You'll divide both sides by 5 and isolate x. The key sequence, 100 times 0.075 divided by 5. And I get 1.5, and the unit that we come out with is a milliliter, since we had a milliliter on this side. Excellent work. A drink sold in a health food store contains 0.50% weight by volume of vitamin C. What volume would you have to ingest to obtain 1,000 milligrams of vitamin C? Let's take this very definition. 0.5% tells me there's 0.5 grams of vitamin C contained in 100 mils of solution. That's the definition of percent weight by mass, grams in 100 mils. Set up your ratio, set up a proportion. We would like to obtain 1,000 milligrams, but keep in mind, this has to be a gram, not a milligram. And that's to keep the units the same on both sides. So we remember that milli means 1,000. And so when I say 1,000 milligrams, it's the same as saying 1 gram. So 0.5 grams is to 100 mils as 1 gram is to X mils. Solve for X. You're going to cross multiply. 0.5 goes with X. 100 goes to 1. We want to isolate the X, so we'll divide both sides by 0.5. X is going to be found by taking 100 divided by 0.5, and we get 200 milliliters. Doesn't that make sense? If half a gram is contained in 100 mils, 1 gram would be contained in 200 mils. And we should probably check, yeah, we'll just put a decimal to make it significant. Another unit that we can relay concentration for very small particles are called parts per million. You'll see that abbreviated as PPM, parts per million. So just as we said a moment ago that percentages means parts out of 100 parts, parts per million means parts out of 1 million parts. And a million, of course, has 6 zeros. Parts per million is found by taking the mass of the solute over the mass of the entire solution. And if I'd want a percentage, I would say times 100. But if I want parts per million, I'm going to multiply by 1,000,000. You can have mass or volume parts per million. What is the concentration in parts per million of DDT? This is a very famous chemical that has been banned. It's been found in the tissues of seabird that contains 50 milligrams of DDT in 1,900 grams of tissue. DDT is a non-biodegradable pesticide, and it persists and is an environmental pollutant. It has been banned in the U.S. since 1973. We have 50 milligrams of this active ingredient, DDT, in every 1,900 grams of tissue. Now, before we calculate, we have to convert into like units. Remember, I need to have grams over grams. And a milligram, milli means 1,000. So we have to take that 50 and move the decimal spots 3 points to the left. 50 divided by 1,000 is going to tell us that's 0.05 grams. So 0.05 grams in 1,900 grams of your tissue expressed in a parts per million. So my key sequence says to say times 10 to the 6. Type in 1 with 6 zeros. 0.05 divided by 1900 times 1 million. And this right here is your scientific notation key. Some of your calculators use 10 to the x. Some of your calculators have EXP, and some of your calculators have EE. All three of those buttons are just dependent upon your style of calculator. They're all the same thing. It represents times 10 to the 6th power. Or you can literally hit 1 with 6 zeros and hit equal. That's 1 million. And when I do that, my screen reads 26.3. Oh, let's consider sig figs. Looks like we have 2 sig figs there, so we'll say 26 parts per million, ppm for parts per million. Instead of multiplying by 100 for a percentage, we multiplied by 1,000,000 and got parts per million. Should you try some on your own with parts per million? Take a read through these problems setting up your work. Remember that I'm looking for work shown as I'm looking through your note packs for credit. So pause the video, come back to me when you're ready to check. Okay, this is really a metric review, isn't it? You must still have memorized your metric prefixes. Must keep memorizing, perhaps, must keep memorized the metric prefixes. Note to self. Letter A, 0.042 milligrams in 1,400 grams. Now remember, I must have gram over gram. So I have the bottom one in the correct unit, but I've got to switch over the top one. So in 1 gram, we know that milli is 1,000. So we have to move that decimal place over 3 spots to the left. It's going to get very small. 0.042 divided by 1,000 gives me 0.1234042 grams in your 1,400 grams of solution, and then multiply by 1,000,000, and we get parts per million. So 4.2 times 10 to the -5th is the same as saying 0.000042. Divide that by 1,400 and multiply that by 1,000,000. That's 1 with 6 zeros. And you get 0.03 parts per million. Letter B. We have 5 times 10 to the -4th grams in a kilogram of minnow tissue. How many parts per million is DDT in this particular tissue? We have the top unit fine. We're already in grams, but the bottom unit needs to be converted. So kilo means 1,000. I know that 1,000 grams is the same as 1 kilogram. And so on the bottom here, we have to make sure we're using 1,000 grams on the bottom. So on my calculator, 5e -4. Think about what that means. It's 1, 2, 3 zeros. That's supposed to be a decimal. I'll make it clear. 1, 2, 3. And if the 5 is right here, 1, 2, 3, 4. That's 5 times 10 to the -4th. So that's 0.0005. 5 times 10 to the -4th divided by 1,000 multiplied by 1,000,000 and I got 0.5 parts per million. How did you do? Is yours matching? Make sure you're practicing with your key sequence if it's not. Here's what I'm looking for, letter C. Letter C gives us 2 milligrams in a kilogram of needlefish tissue. We got work to do on both parts, don't we? 2 milligrams, I keep losing that, in a kilogram. So as I'm going to make sure that I get gram over gram, just make yourself a note, must be gram over gram to express, then times 1,000,000 to get parts per million. So we've got converting on both sides here, top and bottom. So we know in 1 gram, there is 1,000 milligrams. Milli means 1,000. So that 2 is going to get divided by 1,000. You're going to move the decimal point 3 spots to the left, and you get 0.002 grams. We know kilo is a large unit, that it takes 1,000 grams to give us a kilogram. And so on the bottom, we have 1,000 grams. We multiply that by 10 to the 6th power, or 1,000,000, one with 6 zeros after it. 0.002 divided by 1,000 times 1,000,000. And our answer is 2 parts per million. There was one more, a letter D. What did it say? 225 micrograms. That's that little squiggly U. It's a micro. 225 micrograms in a kilogram of tissue. Now just to remember, 10 to the negative 6 is a micro. And that's the unit there that is representing that squiggly U. So we've got to convert that into a gram. I know that 1 gram would contain 10 to the 6th micrograms. That's the bigger unit. 1 gram takes 1,000,000 micrograms to give me a gram. And of course here, kilo is the larger unit. So here we have 225 divided by 1,000,000. And you come up with 2.25 times 10 to the negative 4. Or maybe your screen is reading 0.000225. That's the same number. One is called scientific notation. And this is just called standard notation. They're both the identical number. And that's going to be placed over 1,000 grams. And then we have to multiply by 1,000,000 to get a part per million. 2.25 times 10 to the negative 4 divided by 1,000 multiply by 1,000,000, and you get 0.225 parts per million. A lot of zeros to keep track of with parts per million, such a small number. A much more familiar unit for concentration to a chemist is called molarity. Molarity is defined as the number of moles of solute per liter of solution. Moles of solute per liter of solution. Now let's remember what we remember for our mole map. I'm going to show you what I would say is just those round little buddies. That if you draw this with me, you can see visually our definition of mole per liter, and big M is going to be molarity. And liter is the volume of your solution, and mole, of course, is the central unit of all of chemistry, the mole unit. Now, another unit that we often measure in is the gram. And just bringing back an old mole map problem, a mole is defined as the grams over the molar mass of our substance. So these are two visuals for the formulas. And remember the trick? If I'm asked to solve for moles, that's the one I cover up, don't see it, and I can see m times L. So just cover the variable up that you're looking for, and you can see the algebra coming out. And I also wanted to say, notice that the mole unit is contained in both of these round little buddies. Alrighty. So the mole is the central unit between grams and molarity. Let's try some of these out. Calculate the molarity of a solution. So this is big M, the molarity, big M. Concentration unit defined as moles of solute per liter of solution. But we went to the scale and we weighed out 20 grams of sodium hydroxide and 250 mils of solution. So I'm going to just redraw those round little buddies a moment, just from the previous page. And I just want us to remember what this stands for is molarity. It's a concentration unit for moles per liter. And the other one I just drew is the round little buddy for calculating moles. That grams over molar mass is our definition of a mole. So let's take just a visual here of what we know. From the problem, I had 20 grams of sodium chloride, NaCl, sodium hydroxide. I'm glad I corrected that. That was given to me right here, is 20 grams. And you know what else I know? I know the molar mass of sodium hydroxide. If I just go to the periodic table and I find the atomic weight of sodium, 23, oxygen weighs 16, hydrogen is 1. You see how I'm just giving these whole numbers? 6 plus 3 is 9, plus 1 more is 10, 3, 4. The molar mass is 40 grams per mole for NaOH. That's the number I know right here, 40 grams in every 1 mole. So when I solve for mole, cover this one up, I can clearly see to solve for mole, I would say 20 grams divided by 40, and that's 1/2. So I found the number of moles first by taking grams over molar mass. This was the roadway between the scale and the mole back when we looked at a mole map. 40, remember yourself, is just me calculating molar mass of sodium hydroxide. So now that I know that this is 0.5 moles, I can have 0.5 moles brought over into this area. That's what I just solved for, 0.5. And the volume of 250 mils has to be converted into a liter. And that's just reminding yourself you slide the decimal 3 spots to the left. So 0.25 liters goes into that spot of your round little buddy. So your molarity, big M, would be found by taking 0.5 moles and dividing by 0.25 liters, moles per liter. What is that? Whoops, calculator on. 0.5 divided by 0.25, and that's 2 molar. Let me just say how you would read that. You would say 2 molar. That's what capital M stands for. The molarity unit is 2. 2 molar is its concentration. So step 1, we found the number of moles. And once we found moles, we brought it over to this round little buddy and solved for molarity. Excellent. Should we try another? What is the molarity of an intravenous glucose solution prepared from 108 grams of glucose in a 2-liter solution? Do you remember glucose is C6H12O6? That would have to be prior knowledge because it was not given in the formula here. Where do we start? Well, here I'm going to redraw my round little buddies. Hopefully the more you draw them, the more familiar they get. You have to know these. Moles per liter is big M. Big M stands for molarity, the concentration unit. Our second round little buddy says grams over molar mass gives us the term mole. So let's record what information we were given. We were given 108 grams of sugar. So there's the grams in this portion of the round little buddy. You know what else we know? We know molar mass because we know the formula C6H12O6. Carbon has a formula weight of 12 and there's 6 of them in the formula. Hydrogen has a molar mass of 1 and there's 12 of them in the formula. Oxygen has a formula weight of 16 and there's 6 of them in the formula. Let's sum all of the atoms together. 12 times 6 plus 1 times 12 plus 16 times 6 gives us a molar mass of 180 grams. And that goes right here. 180 grams is the molar mass. So to solve, you can see that we would say a mole is equal to 108 grams divided by 180, where the 180 was the molar mass from our formula. What is that? 108 over 180 is 0.6. So that's what we solved right here, 0.6 moles. And remember, that's what we can bring over to this now, is that we have 0.6 moles. We have 2 liters of solution. Let's solve for molarity. Molarity would be the 0.6 moles divided by the number of liters, divide by 2, and we would come up with a 0.3 molar solution. You would say 0.3 molar is how you read that capital M, a concentration unit of moles per liter. You have some practice here, calculating the molarity of each in an aqueous solution. These are all the same solute, NaCl, and look how nice they are. They gave us the formula weight called the molar mass and the final volume. Calculate the molarity. You remember your round little buddies. Molarity is defined as moles of solute per liter of solution. Moles is defined as grams over molar mass. Go to work and come back when you're ready to check. Hi, welcome back. Are we ready to check some work? In letter A, we have 1 mole of sodium chloride in 0.5 liters. Moles per liter. We didn't need to do any gram or molar mass calculations. 1 divided by 0.5 gives us 2 molar. Letter B. 2 moles of sodium chloride in 250 milliliters, which is 0.25 liters, must be a liter. Remember that there is 1,000 milliliters in every 1 liter. So I'm just moving the decimal spot 3 spots to the left, 0.25 liters. 2 divided by 0.25 is 8 molar. Letter C, 0.05 moles in 5 milliliters. 1, 2, 3, that's 0.005 liters. Move the decimal 3 spots from the left to turn milli into a liter. 0.05 divided by 0.005, and you have 10 molar. Letter D. 12 grams of sodium chloride. All right, now here, let's just kind of get our bearings. Sodium chloride is given to me as 12. The molar mass, 58.44. So you see what I have to do first? I'm going to solve for mole first. 12 grams over the molar mass of 58.44. So I'm finding 12 divided by 58.44, and that's my 0.20533, so I'll say 0.21. And then I can bring that over here. It's in a volume of 2 liters. So here's my step 1, solve for moles. Step 2, I'll solve for molarity. 0.21 moles of solute in 2 liters of solution. So I just need to divide by 2. And that comes out to 0.1026, so I better 2 sig figs, 0.10, that's it right there. Big M, that's 2 sig figs. And 0.0 or 0.10 molar is how you would read that. How about letter E? Give myself some room. 24.4 grams divided by the molar mass of 58.44 is going to give us moles. 24.4 over 58.44 is 0.4175. I'll put that as 2 decimals or 2 sig figs. And then that number of moles, so here's your step 1. Here's your step 2, the number of moles of solute per liter of solution. And that was given to us as 350 mils, right? 350. So that's 0.35 liters. .42 divided by 0.35. This looks like 1.19. I'll round that to 1.2 molar units. How about your letter F? Let me scroll up to find it. Letter F. 60 grams of salt, 60 grams of NaCl, which has a molar mass of 58.44 grams, is going to solve for my number of moles. 60 divided by the molar mass is 1.026. I'll say 1.03 just for this moment. So step 1, get the moles. Step 2, divide the number of moles by the volume in a liter. So I'll divide that by 0.75, and my answer is 1.37, and that's 3 sig figs. That's good enough. There's the molarity for letter F. Take a moment and process. My dog wants up on my lap. Shall we try another? Targeting another variable. How many milliliters of a 0.3 molar solution of glucose contains 0.025 moles? Let me get this little round little buddy. We know that moles per liter is big M, molarity. So what were we given in this story problem? We were given 0.3 molar. We were given 0.025 moles. We want to know liters. So when I think about setting this up, the volume in a liter will be found by taking 0.025 moles and dividing it by the concentration unit of 0.3. So when I hit this, I would say 0.025 divided by 0.3, and this tells me 0.0833 repeating. But remember, we were asked for milliliters, so I'm going to multiply by 1,000 to convert that out. So just move your decimal 3 spots to the right, and you find 83.3. We need 2 sig figs, so 83 milliliters. All with our round little buddy. What do you think? Time to process? Give yourself a moment to think. Review those steps. Moles over molarity pulled out the liter unit from our round little buddy. Let's practice some of those. Pausing, give yourself some think time. Pause and think. Come back to me when ready to check. Okay, you must be ready to check. Remember the round little buddy. Moles per liter is big M. So we're looking for the volume. It will come to us in a liter, but we can simply move the decimal 3 spots to find the volume in a milliliter. We want the mole over molarity, and that gives us the liter unit. So for example, in letter A, 0.15 mole in the molarity of 1.5. Now that's going to be given each time, right? That's the same number each time. And then when I get this answer, 0.15 divided by 1.5, it gives me 0.1 liters. And just remember that there's 1,000 milliliters in a liter. So just move your decimal 3 spots over to the right, and that gives you 100 milliliters. 0.02 moles in the concentration of still 1.5. When I hit this out, 0.02 divided by 1.5 is 0.0133 repeating. But I want that to be in a milliliter, so remember to slide your decimal 3 spots to the right, and you will find 13.3 milliliters, or 13 with 2 sig figs. 0.003 moles. Concentration is still the same, 1.5 molar. 0.003 divided by 1.5 is 0.002 liters. Slide that decimal 3 spots to the right to convert your liter to a milliliter, and you have 2 milliliters. And the letter D, 3 moles in 1.5 molar solution. 3 divided by 1.5 is 2. Remember to multiply by 1,000, moving that decimal 3 spots to the right. So 2 times 1,000 gives you 2,000 milliliters. Give yourself a big old star. It just feels good. You're doing great. How many moles of sodium chloride are contained in 710 milliliters of a 0.15 molar solution used for rinsing and storing contact lenses? Same formula, we just have a different target. This time, we'd like to know moles. That's our target. The volume is 710 milliliters, and the molarity is 0.15. So if I want to know mole, I need to take molarity times liter. And remember, to get this back into a liter, we have to divide by 1,000. So this, moving your decimal 3 spots left, is 0.710 liter. So we want to know moles. Moles will be found by multiplying the number of molar units times the liters, 0.15 times 0.71, and we find 0.1065. Let's just say that's 0.11 moles. All different ways of solving for the round little buddy. How you doing? Practice some of those as well. How many moles of table salt are contained in each volume of aqueous sodium chloride? Pause your video, give yourself some think time. Come back to me when ready. Welcome back, letter A. Remember our story problem here. We want to know moles, so we know it's molarity times liter. Not milliliter, but liter. 2 liters times 2 molar will give us 4 moles. I should write that as 4.0 moles to have 2 sig figs. Letter B. 2.5 liters times 0.25 molar. What'd you get? What's 2.5 times 0.25? 0.625. I'll give that 2 sig figs. 0.63 moles. And letter C. 0.025 liters times 2 molar. Remember, this has to be brought over 25 mils. You're going to divide by 1,000, and that's where I got 0.025 liters from. 0.025 times 2, and that's 0.05, and I better make that 2 sig figs, so I got to put another 0 there, and that would be moles. And one more in this stretch. 0.25 liters, right? 1, 2, 3. 0.25 liters times 0.25 molar equal, and that's 0.0625. I better give that 0.063 moles. Super awesome. Now, let's bring this back together with both round little buddies in this sample problem. Let's give it a read through. How many grams, this is what I want to know, of aspirin are contained in 50 mils of a 0.05 molar solution? Here's what we know. That the definition of molarity is moles per liter, big M, molarity, the concentration unit. We also know the definition of a mole is grams over molar mass. It's our old mole map problem. So let's figure out what we know. Well, this is what our ultimate variable is. Well, this is our target, right? We want to know grams, so that's where we'd like to land. Let's put in what else we know. We know the volume is 50 mils, but I can't put in a milliliter, so I have to move that decimal to get it back to a liter. So I move it 3 spots. It's 0.05, oops, I should have an equal. 0.05 liters. So I know that 0.05 liters is 50 mils. I also know the concentration is 0.05 molar units. That's big M. You know what else we know? We know the molar mass. It was given to us as 180.2 grams per mole. I think we have enough information to solve for grams because I can find mole in my first step by taking molarity times liter. My 0.05 molar times 0.05 liter. What do we find? 0.05 times 0.05. That's 0.0025 moles. Well, that's what this is right here, 0.0025 moles. So now we know this. And I can find grams in the next round little buddy by taking the moles times the molar mass, which is 180.2. I forgot that part. 180.2, and that gives us 0.4505. I'll make that 2 sig figs, so 0.45 grams of aspirin? What do you think? We did molarity times liter to solve for mole. That was our step 1. Once we knew the mole, we brought it over to this round little buddy and pulled out grams. You need to recognize both of those formulas and be able to manipulate for any of those target variables. Same idea. Pause and think. Solve for how many grams of table salt are in each one of these following volumes and given the concentration of 1.25 molar. Pause and think, come back when ready. Okay, how'd you do? Well, here's our strategy. We know that molarity times liter gives us moles. And then we know moles times molar mass, whoops, only one L, is going to give us our gram. And so we have a 2-step story problem. Step A, 1.25 molar times 0.1 liter. Now that's 1.25 times 0.1, and that's 0.125 moles. Step 1, we solve for moles. Step 2, 0.125 moles times the molar mass of sodium chloride. And didn't we just keep using that over and over a little bit ago? 58.44. It sounds so familiar. I'm going to go back and grab that. 58.44. .125 times that formula weight of 58.44. And did you find 7.305? We'll say 7.3 grams of sodium chloride. Perfect. How about letter B? 1.25 molar times the volume of 2 liters gives us the number of moles. And that's 2.5 moles. Then we take the number of moles and multiply it by the molar mass, and we find our grams. Except it's not 0.25, it's 2.5. I had that on my screen already. 2.5 times 58.44, and I have 146.1. We'll just leave that as 146 grams. Letter C, 1.25 molar times 0.55 liter gets us number of moles. Carrying those decimals, and we'll just round at the end. I'll multiply that by the formula weight, and we get 40.17. I'll say 40.2 grams of sodium chloride. And here I'll put a letter D. The 1.25 molar times 0.05 liter is 0.0625 moles. I'll just round at the end. 0.0625 times our formula weight of 58.44. And that's 3.65. I'll leave that as 3.7 grams of salt. Give yourself a big old smiley face. It just feels good. We've been doing all kinds of hard work with molarity problems.
one.
Yeah, I did catch that one. So let's model another one. How many milliliters? Okay, so I'm going to get my bearings straight. I know that my round little buddies involve the following formulas. Moles per liter is molarity, and I know grams over molar mass is a mole. All right, those are my two visuals that are helping me in this section. All right, so let's just plunk in when we read numbers where they go. How many milliliters? So this is ultimately what I'm looking for. I'm given a 0.25 molar solution, and I'm going to be given a variety of grams right here, and the molar mass is given to me as 342.3. And you know what? Ultimately, what we need to do first is step 1, solve for moles. And we'll do that by saying grams over molar mass. And once we have moles, we'll take the moles that goes over here then and divide by molarity, and that will give us liters. And when we say solve for liters, multiply by 1,000 to get it into the milliliters it asked for. So for instance, all that's going to change in this process is the grams that we start with. In the first example, we're given 0.5 grams. So let's just place that right here. 0.5 grams over 342.3 grams. 0.5 divided by 342.3, and the number of moles is 0.00146 moles. And so of course that gets brought down here. 0.00146 divided by 0.25. This gives me 0.00584 liters. And I'm just going to slide the decimal by multiplying by 1,000. And we get 5.84 milliliters. Step 1, we solve for moles. We do that by taking grams over molar mass. In step 2, this was all for problem 1, we said the number of moles divided by molarity pulls out liters, and then of course from there we can slide it to a milliliter. In your second problem, we start with 2 grams. 2 grams of salt, still over 342.3 molar mass, and that's going to give us the number of moles. From there, 2 divided by 342.3, there's our step 1, solve for moles. Step 2, take the number of moles, and I want you to divide by the concentration unit, molarity, which is always going to be 0.25 in this story problem, and that's going to give us liters. So I'll divide by 0.25, and remember, it's right on your screen, multiply by 1,000 to just move that over to report it as a milliliter. So right while it's on my screen, I'm going to multiply it by 1,000. I get 23.37. I'll round a little bit and get 23.4 milliliters. How about the third story problem? This time we're given 1.25 grams of sucrose. I'm still going to divide by the same formula weight, 342, and that's going to be a mole unit that comes out for me. 1.25 over 342.3 is 0.00365 moles. Step 1, solve for moles. Step 2, we'll take that number of moles, and I want you to divide by the concentration unit given, 0.25 molar. Knowing that that's going to give me volume in a liter, I want you to just slide that decimal 3 spots to the right, and answer this then as a milliliter. So divide by 0.25 times 1,000. This gives me 14.6 milliliters. This gave us 50 milligrams. Now think about that. This has to be in a gram unit. The gram unit, we're going to divide that to make it smaller, right? 3 spots to the left is going to be 0.05 grams. I must have a gram unit in my mole map. So 50 milligrams is 0.05 grams. Still dividing by the same molar mass. Step 1, solve for moles. Here I get a really tiny number. It's 1.46 times 10 to the negative 4th. Maybe your screen says 0.000146. That's the same number, just in decimal form instead of scientific notation. We're going to take that number of moles and divide by the molarity. And it's always been 0.25. And that's going to come out in a liter, but remember we were asked for milliliters, so just multiply by 1,000 and you'll have your answer. So divide by 0.25 times 1,000. And my screen reads 0.584. I'll have 2 sig figs, 0.58 milliliters. Whew, all kinds of good work. Wow, is your hand cramped like mine? This is a great place to stop the video, stop the lesson, give yourself a little break. Come on back for some more lesson. We have dilutions and colligative properties still waiting for us, but it's important to take a break. Give yourself some think time and pause.